All right. First of all, now we go back to bridges, and I want to talk about the modeling and analysis of the bridge structure. We talked about the overall things, so let's get into the real, problem of how do we model and analyze bridges. And this is the traditional way. Traditional means that most people have been doing or do the bridges this way. Of course, we will not do the traditional way, naturally. But traditionally, the first step is that people analyze the deck and superstructure for gravity loads. So the top of the slab or the deck, they analyze for light load, for vehicle load, for deck load, self load, and then they transfer the reactions from that superstructure to the substructure, pylons and columns and piers, and then they analyze the substructure for lateral loads, earthquake and wind and braking and acceleration and all of that kind of stuff. And after that, they transfer those results to the foundations to design the foundation. So there is one analyze, transfer. It is done in 4 steps. This is the way most people have been designing or handling the bridges. I'm not talking about big bridges. I'm talking about normal, standard, small bridges. However, we will not do this. And I will tell you why not. So the question is, why do we want to treat super, substructure and foundation separately, especially for the analysis purpose? Because we will see that does not make a good sense, right? So we are going to challenge this approach. If you look at the substructure and the superstructure, most of you have seen a lot of them. So that is the superstructure, that is the substructure, and they are connected by bearings, or they are sometimes connected by real connections or connected by bearings. So and people assume that the slab will transfer the load to the girders, and girders will transfer the load to the top of the pier, and then pier will transfer the load to the pylon, cap will transfer to the column will transfer to the foundation. However, this bearing and other connections, they behave in a different way. And also the depth of the girder is a interesting thing, because dead load and wheel load is applied on the top, but the reaction is here. So bearing is, if you draw a beam and put a pin support, you will see that will be here. Center line of the girder is here. Slab is here. Bearing is here. So the load is not applied to the center line and the support is not in the center line. They have a big difference between them. And this big difference can cause major difference in the behavior. And then also we have to see that how the diaphragms will affect that. So let's look at so I made a very simple example to start with. So it's a 20-meter long bridge with a girder 1.6 meter and pile cap, 2 piles here, a pier. Very simple one-span bridge you can think of. And let's see how we analyze it and what are the issues in this bridge design. Normally people will take the load and use this pin and roller or pin and pin, and then transfer, design this one, design 3-4 steps. First of all, that is what people might do. They might model this as a girder supported by pin and roller. Most people will do that, and then apply the load and then calculate bending moments and deflections and reactions and deflections. That is what people would do. Let's look at another issue. And now, as you can see, that the supports are assumed to be at the center line of the girder. Load is here, actual support is here, actual load is here, but we assume the load and support to be at the same level. They are not. Much different. Load and support are 1.6 meter apart. But in this model, we assume them to be at the same level. So if you do that, you will see these are the forces. You do not get any horizontal reaction, and you also get displacements like this. And you get the support, this roller moving in this direction by 0.15, whatever unit that is. Next step. Pin. Instead of pin roller, we assume that the supports are pin-pin. People can assume pin-pin or pin-roller. Because bearings are not rollers. They have some resistance, shear resistance. They have stiffness. So they are whether pin or roller, we don't know actually. But pin-roller is one assumption. Other extreme assumption is pin-pin. So if you use pin-pin assumption, you will find that the results are not different in this case. Because it's simply supported, no difference. Correct? So whether you use pin-pin or pin-roller, you get the same result. So people don't really care which one they use. Both give them the same results. So it doesn't matter. Let's come to the next. This time, what we will do is that using the modified pin roller, that means we will actually not model it at a center line, but rather we will model the bridge girder like this, including the depth effect, moving the support away from the center line. Because the support is not at the center line, it is at 0.8 meter or 0.7 meter below that, right? So we attach a small rigid element to represent the end of the girder, and then we put the support where it is physically located, right? And now, so I'm still assuming that the load is actually here, but I'm assuming load is here, but in fact that part is not, only half the part is corrected for now. Only the center line to support location is corrected. And now if you apply this one and use a roller and pin, you will find that you also get a U1 reaction. You also get a horizontal reaction, which was supposed to be 0 before that. I mean, you also get a horizontal displacement, which was 0 in the previous one. If you go back, you will find that U2 is 0, except rotation, all others are 0, right? But now when you do that, you see that this end of the girder is going to move because it's not straight. So this roller will move now. As this deforms and this rotates, the roller will move. The roller will not stay. So you have a displacement of that many millimeters on the right side. You understand, right? So, which means that now we have a different results from the previous one simply by correcting for the support depth. Now let's go to next step. And if I use pin-pin, then you will see that of course the displacement will be 0 because you use pin, but now you will have horizontal reactions developing here, which were 0 before. Because if you have a roller, it will move. If you have a pin, it will not move, but horizontal reaction will develop. Which means that the reactions on the substructure will now be different. So now, whether you use roller or pin changes the results. In one case, you get horizontal forces. In another case, you get horizontal displacement. Reality is neither pin nor roller. It's a spring because bearing is a spring. So it has a certain shear stiffness, right? So which means that now we cannot assume roller or pin because both of them are giving you different results and both of them are incorrect because bearing is not a roller and bearing is not a pin. Bearing is a spring which has a stiffness. So which means that the modeling of the bearing becomes important even for gravity load. Forget about the lateral load. Of course, it will be very important for gravity lateral loads. But even for gravity load, for dead load, live load, the modeling of the support needs to be correct. And the traditional approach of using pin roller is not going to be correctly representing the real behavior. Right? So we can start to see that we cannot use the separated that, and we actually now will see that this stiffness is not only the bearing rollers, the bearing stiffness, but also the pier stiffness and the foundation stiffness. Everything is holding it together because the displacement at the top of the pier will cause bending in the column that will move the foundation, which will move the soil. So this horizontal support is coming not only from the bearing, but everything below the bearing because bearing is resting on something. So it's it's becoming a little bit more complicated now. So which means that we should remember that we are actually trying to solve this problem, and that problem was not represented correctly by the line element or line model that we saw with the roller and pin. We should go back to the real bridge to try to find the behavior. Now let's complete, so which means that let's add the piers now. So let's combine the beam and the piers together, and we link them by something, because they are not fully connected, they are not framed. So if you look at it again, they're not directly connected, so you cannot have a rigid frame. It's not a building frame, it's a bridge, which means in this case, there has to be some kind of a connection here to represent the bearing. And now if you apply this frame here, then you will find that, okay, you will get negative moment, but that is not correct. This is for a building which is fully connected. It's not fully connected. Girder cannot transfer the bending moment to the piers because there is no moment connection there. There is no reinforcement going through there. So this is actually incorrect. So if you model the frame thinking that I'm going to model that as a frame, you will again be wrong because it is not correct. So which means that now we need to modify this connection in such a way that the moment is not transferred, but horizontal forces are transferred to that one. So with moment release, we release the moment at the end because there is no moment at the end. So we say no release, no moment at the end. We go to SAP and we release the moment at the end. So this portion does not transfer moment. Moment will be zero. But the reactions and horizontal displacements will be now correct because but right now we are still assuming that the bearing is a real connection. We are not replacing it by a spring yet. So I'm talking about step by step. So we model it, but we release the moment, so we solve the problem of the bending moment, but we did not solve the problem of the flexible connection. We are still assuming that the girder is fully connected to the pier, which it is not, right? But you can see that step by step we are trying to make it more real. So now we have solved the problem of the moment. And now we go further, we create a full model. We go down to the pile, we come to the footing, and we say, okay, the whole thing. Why not we just model everything and not the pier? Because pier, below the pier, in the previous example, we have used a fixed foundation, but this is not, pile cap is not really fixed. It also can move. Nothing in this world is fixed or pin or roller in reality, except a real physical steel roller that you might have seen in some bridges, but normally for real concrete bridges, there is nothing like fixed pin or roller. It is always something in between. So we are trying to model the real bridge as much as possible. So this fixed support actually is not representing correctly the soil conditions and foundation. So that's why we decided to go on and make it a complete bridge. So now we have, and then we put the pin at the bottom of the pile, which is a very realistic assumption. Below that, pile does not move, so it's fine. And horizontally, we will add soil springs here to represent the soil on the pile. So which means now our model will be more comprehensive and complete. And also, we will replace the link between this one and this one by a link element, a spring. So then we add a spring to represent the bearing. So then our model will be complete. So girder will be represented like that, but also with the end to offset for the support. Between this one and this one, we will add a spring, and this one we will add this one, and we will also have soil springs. Then we have soil, bearing, girder, piles, pier, deck, all complete in the same model. Then your model will be realistic, and the same model can be used for gravity load. Same models can be used for temperature, for braking, for earthquake, for whatever you want to do. So you do not need separate models for that, right? And we release various things here, and then we try to create the model as And then you see that, okay, now you get for gravity loads, same as spin roller, nearly same as spin roller condition will be obtained, and we get some movement, but now it's more accurate because it's not a real roller, but the displacement will be different. But we have some bending moment in the column coming from that displacement, so that roller is moving the column, so column will try to bend, so we can calculate. So which means that vertical load on the girder will actually create bending moments in the pier, which otherwise you cannot imagine if you use a simple fin roller condition. Because the girder is not modeled at a center line. Girder is deforming, is rotating, that rotation is moving the bearings, that movement of the bearing is causing the column or pier to move and causing bending moment in the column and foundations. So this bending moment there, but you also get reactions, so you get the whole thing in one go. You get pile forces, you get everything in one go. What about lateral loads? So if you apply a lateral load on this one here due to breaking or earthquake or anything, you can see that now you are able to represent this whole thing, and then you can see that the bending is not right. This is causing a bending like this, and this is causing bending like this, depending upon where you release the moment and where you did not release the moment. So now you get different bending moments on two direction, two location. If one side is released, one side is not released properly, then your forces will be different, reactions will be different, bending moments will be. So two sides are not going to be equal, depending upon where the bearing is placed and where you use the pin and where you use the spring condition. But in fact, reality is both are bearings. Both are going to have the same kind of behavior. So this model is still not very correct, but because we have not modeled the bearings properly yet, as springs they should be. So when you put the springs with a real spring stiffness, then you will find that the behavior will be even more different than the previous one. So we're trying to go step by step and improve the model. So this is full model without bearing, and then we have seen that these are the problems because the two sides are not behaving symmetrically. They are not symmetrical depending upon where you have put the release, where you haven't put the release, where you have put the bearing to be released and where you haven't put the bearing to be released. So what can we note? What we note is it is possible and preferable to model and analyze the super and substructure together. That's first thing. We cannot assume that super and substructure are separated. They are connected. And depending upon the type of connection, we can continue to model them as bearing, as fully connected, as whatever connection is there, we just model it. Even if it is rigidly connected, we just model it. If it is simply supported, we model it that way. If it is bearing, we model that way, but we complete the model as one. We need to take care of connection between deck and substructure parts, connection between piers and footings, interaction between footing, piles and soil, especially complex behavior at the abutments. So when we go to abutments, end of the bridge, it becomes even more complicated. So key issues are bearing modeling, soil modeling and boundary condition, right? So which means that when we are doing the bridge modeling, we try to be as complete as possible. The conventional or old method of separating the different parts of the structure and transferring the load and then doing that is not efficient, it's not accurate, it's not realistic. So we should always try to create the full model of the bridge as much as possible. Right? That is the lesson number 1 from this. Now we will go to how we can model each thing more accurately and how we can then complete the analysis of the bridge in more realistic manner. So this is just a very simple example, does not contain everything. I did not model the soil, I did not model many things. I did not model the bearing. I just explained to you that these things need to be modeled, and if you don't model, the behavior will be different. Okay? Let's look at another example now. Link elements to model a bearing. So I'm now creating a bridge, a little bit more 3D. That was 2D model of a bridge. Not even complete. There was just one girder, one side. Let's look at a real 3D bridge. Not real, but a 3D bridge, 3D model of a bridge where we have a pile. So please notice here, that is the pile, the pier head, that is the pier, that is the foundation, that is the diaphragm at the end of the girder, that is the bearings, 3 bearings here, 3 bearings there, those are the diaphragm, those are the girder. So we try to model everything in a shell element model, not even beam element, because then we don't need to have those link kind of things. It's real. So it is very close to the real bridge now. We have modeled the slab at the correct location, we have modeled the girders, we have modeled the diaphragms, we have modeled the bearings at the correct location. Everything is more or less physically correct. So this model should give you much better, much realistic results than the previous one, because we don't need to make any simplifications. Everything as it is in the model. Like I said before, you should model what is real or build what you model. Do not have difference between the two. A lot of people make simplifications either in the model or in the construction. For example, I've seen many engineers do that. They get a lot of torsion or bending moment that they cannot handle. They assume a pin or release the moment over there to solve their problem, but they do not construct accordingly. They do not stop the reinforcement. They do not make the link at the site. So the site is still behaving connected, but just to solve their problem, they assumed a pin over there. But they did not construct the pin at the site, so it doesn't matter. It makes no sense. Same as the case, if there's a pin at the site, or there's soft connection, or a release, or a spring, you must model it. So remember always, model what is there or build what you model, but do not have them different. Otherwise, it's no point. You're just fooling yourself by making model simplification that do not exist. So we always try to model realistically whatever you have. At least make sure that everything is included. Even if it is rough, it should be there. So now with full model, we have put a spring here. This spring can be a linear spring or can be a non-linear spring. So modeling of the complete thing realistically, including non-linear effects, everything is actually requires a lot of understanding. But let's remember 2-3 important things. First of all, slab is not at the center of the girder. Slab is away. This problem has been bothering the engineers for as long as, before SAP, before all of that, when we did not have these tools. When I designed some bridge very long time ago, I realized that what we are doing is wrong. And I could not find a way at that time to solve this problem. So we developed many simplified methods. And first, how to take this offset into account, that the depth, the slab is away from the bearings. That is something not new. People have known this for many years, at least 30 years, 40 years, 30 years. But they didn't know how to solve this problem until we get this 3-dimensional modeling tools available. So I used all kind of rough things to try to accommodate, put a truss there rather than a beam, and do all kind of stuff to be able to do that. But now we can model it realistically using either shell element or offsets, physical or use the constraints. So we can do many things. There are many tools you can use to take care of this offset. But the point is that this modeling of the deck, how to model it correctly, what elements to use, what to use here, is a lot of work to understand completely, but it matters on the efficiency of the final design and the prediction of the correct behavior. Shell model so we can use the shell model for the bridge pier instead of you can do many things. I'm just telling you physically what is possible. And you can also do this model completely like that. This is a model of Rama 3 bridge, one of the students. When we have a full bridge course, I used to ask them to go to Bangkok, choose one bridge and create a model of that bridge. So people will choose whatever bridge they like and then come back and create a model and try to analyze it. So this is one of the Rama 3 bridge models. You can see everything is modeled correctly as shell and then box girder and everything. modeling of everything. So shell model represents a complete bridge, but it's not always possible to do that. So you can simplify the girders into a frame element, but you connect it to the shell element by using proper offsets and proper constraints. So it just makes it more difficult when you do not model that. But it makes it easy to calculate bending moments into design. So there are always positive and negative points on creating the models. So modeling of solid and hollow pairs with shell elements can be done. Now, what are the practical modeling considerations? Using the right software that supports modeling option being selected, that is very important. You must have the right software. That's why bridge engineers like software speaks bridge. You know that, what I mean, right? SAP 2000 is a general finite element program, but it does not speak bridge. That means it does not know what is a diaphragm, it does not know what is a pier, what is a pile, what is a bearing. You can model everything by using SAP elements, but it does not have any bearing element, does not have any diaphragm. So you cannot look. So CSI could not sell SAP 2000 to bridge engineers because it does not speak bridge language. Just like ETAP speaks building language. You have floors, you have stories, so it speaks, even though the model is the same. Underneath, SAP and ETAPs are exactly the same solver, same everything. On the top of that, they have built two programs. But behind that, it's the same program. One speaks building, and one is a general set. And then, when I started working with CSI a long time ago, I made a presentation to them that why don't they have a program called CSI Bridge, which speaks bridge. So that time we started the work on that, and now they have CSI Bridge, which basically is another program on top of SAP 2000, which simply speaks bridge. That means you can say, this is my bearing. Actually, it converts that into a link element. So you can specify the dimension of the bearing, and it becomes a link element in the model. But you can say, I want a diaphragm here, I want a pier here, I want a abutment here. So it has all the bridge terminology. Internally, they are converted into finite elements, and SAP is used. So you can go directly to SAP and use it, or you can use CSI Bridge because it is easy to model the bridge in CSI Bridge because it has all these deck slab, box girder, so it understands bridge language. And people started buying CSI Bridge a lot, even though it's the same program, but just it has added layer on top of that. So the important thing is that you should be able to model the bridge in almost any program if it has enough power. But having the right software is important. The skill in using the software properly. Obtaining, determining, computing the properties and parameters. This is the most difficult part. If you want to model a bearing, where do you get the properties from? What properties do you need? Right? If you want to model soil, what properties do you need? Where do you get them from? Those kind of things. So getting the properties of the components that you use is a difficult task, and you should know how to get them. For sophisticated models such as DG, the ability to carry out parametric and sensitivity analysis. Okay, we need to, so this is another important thing, that parametric analysis. That means we should be able to refine or find the best combination of the different parameters, and that means that which element, which part of the bridge is sensitive in terms of the cost and behavior. And we for example, soil and pile. So you should see whether the soil properties will affect the bridge much or not. If not, you don't need to care. So normally what we do is we model the bridge and we use the property of soil, then multiply that property by 10 and divide that by 10 and do the analysis. If the behavior does not change much, that means the property of soil in this bridge is not important. We don't need to waste time on that. So we can eliminate the things that we don't really need. So sensitivity analysis is to ensure that we concentrate on the right properties. So this is another sample model. So now you can see from here that this is a 3-span. So not only one span, but 3 spans: bearings, soil, These springs you can see as soil, vertical soil, horizontal soil, bearings, girders, diaphragms, deck slab, piers, pier heads, everything is complete for 4 spans. After the expansion joint, another will start. Right? So you can extend that basic concept to 1 span or multiple spans. Important is that you model all the elements in the bridge as accurately as possible. And if you look at it from the 3D view, you will see that it looks almost as a real bridge. Right? So this is from CSI bridge. You can see that if you extrude the views, everything is almost, so you can see that, okay, this is my bridge. The real bridge is the model itself. I haven't lost anything in translation, or no simplification has been done. Right? So if your model looks like this, you can be confident, or you can, not confident, but you can know that at least you have modeled it realistically. Right? The only thing that is not visible is the soil and the bearing properties that are link elements that you cannot see physically, but they are to be applied properly to the bridge. Now, another example, even the piles are fully modeled. Soil spring here, soil for the pile spring, and then the bearings, little soil on this one, soil. The spring on the pile you cannot see as a spring because you assign it as a line spring, so you don't see it, but it's there, right? And then you have a pin there. So you can see here, bearings are actually separate. There's a gap, physical gap between the bottom of the girder and top of the pier, the way it is really there on the bridges, right? So you can see that it's not one node, it's a gap equal to the height of the bearing. So everything is very real. So this way you can analyze it, and you can get, in one go, you can get the forces in everything. In the slab, in the girders, in the diaphragm, in the bearing, in the pile cap, in the pile, in the pier, and in the piles themselves, and soil pressure also. All in one model. So let's go back to now a little bit more details on how we model the deck. So that's the overall concept, how we model the whole bridge. The deck itself can be modeled as beam element, grid plate model, thin wall model, plate shell model, or solid model. So you can have all these models. And the thesis that I mentioned to you, she basically studied all these models on a bridge and see which one is the best one. So a deck, a real deck, that's a concrete deck, that's a steel girder or I girder or precast, whichever girder that is. So this can be represented by a beam model, just like that, or it can be represented by a grid model, or it can be represented by a beam plate model, or a shell model, or a solid model. Just like you remember in the building, I showed you one table, and I showed you 6 models for that. It's the same thing for the bridge. A simple deck can be modeled in a number of ways. And again, the same question I asked at that time, which one is correct? You remember the answer to that question? What was the answer to the question when I asked the same question about building?
All are correct, none are.
Yes, same answer here. All are correct, none is correct, right? Depending upon how you model it and what you are looking for, right? So it's very important, whatever model you create, you must know what you're doing and what you're missing. And if you are able to handle that, it should be fine. So WL squared by 8 still works. I think this picture is from her thesis. So simple model, only the center line of the deck is modeled as I showed you. Full beam model, every bridge component is modeled by beam elements. So that's a beam element, beam model of a bridge. So everything is modeled, but it is modeled by frame elements, equivalent frame elements. So the bridge is converted into equivalent frame, just like we converted flat slab into equivalent frame. Same thing applies here. So corresponding properties are calculated. This is a bridge in Bhutan, we did that. Of course, the abutment and foundation are still modeled completely. I'm talking about the bridge itself. It's an arch bridge. a grid model is that you model everything flattened. We don't use it too much now. This used to be the most popular method in practice, where the slab and the beams were modeled flattened into one model, both directions, because wheel load can be moved on that one. So grid model we used to use a lot. It was a big improvement over the beam model because it could model 2D behavior, slab and girder. But as you can see, if it's a box girder, converting that into a grid is a very bad model. But for a deck, normal, it is possible. But you flatten them. You move them, you assume that the beam and slab are at the same level, which is they are not. Slab is above the beam. And that created the problem that I mentioned to you. Bearings, every result was incorrect. So grid model, we don't use it anymore, although the option is still there, but it's not that great. So that is a typical grid model. So you will see that the girders, diaphragms and slab, everything is flattened into one plane, represented by beams, and then supported at the ends at the beam level. Beam plate model, instead of the grid, we fill it with plate. But again, not so good, because it does not have in-plane behavior. So same problem that we talked about before, it's not that great, because it has bending, but it's not in-plane. So it doesn't capture the in-plane response of the deck. So again, not so great anymore. Again, same problem. See, the problem that I mentioned to you that keep bothering engineer is that in reality, the center line of the bridge, the bearing and slab are 3 different levels. They are not the same level. But all these models, beam model, grid, beam plate model, they all do not handle this problem, which is a serious one. So engineers have always doubted. So this height difference, h, has always been a problem. So sometimes we will put some artificial beams here, sometimes constrained, sometimes internally. So people have tried many things over the years to handle this problem of the offset. In ETABS, they automatically handle this when you model a slab and a beam. This problem also exists in a building also. The beam is below the slab. So in ETABS, they automatically know that beam is going to be top of the slab. So they put the slab there, they offset the beam center line by internal links. So it's handled correctly. SAP does not handle it. You see, one of the interesting things is that a lot of people, they model the same building in SAP and ETABS and the results are not matching. And they come, oh, the 2 programs are not, one of them is wrong. No, none of them is wrong. Your model is incorrect. Because in ETABS, the difference between the top of the slab and the beam center line is automatically handled. In SAP, you need to handle it manually because it's not a building program. So once you do that correction, the results will match. But most people will not know this. Right? Same problem with the bridge. CSI bridge will automatically take care of all of these things. SAP will not. So if you model in SAP, you have to do these things by yourself. CSI bridge will automatically make all these adjustments. So that's the main difference, because CSI bridge speaks bridge. So, like I mentioned, if it's a plate model, inside it will look like this, because it will model them like this, which is incorrect. It should be like this. So you need to offset the beams down manually. ETABS does it automatically. CSI bridge does it automatically. SAP does not do it, so you need to do it manually. So these kind of things have to be remembered. Shell model, on the other hand, is a complete model. That means that you model the slab and the girders or the bottom, everything in shell models. It's a complete, everything is shell. You divide everything mesh. It's a real, it's a very realistic and correct model. The problem is that then that you do not get bending moments like the traditional one. You get stresses. You need to convert them into bending moments. So, but that's a post-processing. But this is the more complete model. And this is especially very good for post-tension bridges because it's pre-stressed, so you can directly get stresses to design for. And you can put the pre-stressing into the model also. You can put the cables. So it's a very complete model. These days, the bridge models are really quite comprehensive. If you look at them in CSI bridge or bridge programs, they are very realistic. They have everything. They have anchors, they have cables, they have all those stuff. So this is the full shell model for a girder bridge, like I mentioned to you before. So shell model, full shell model, not plate shell, I should say shell model. And it can handle anything. Did I? Yeah, okay, maybe next one. So shell model can handle complicated bridges, curved bridges, skew bridges, variable depth, all those problems that you cannot handle in other models, the shell models can handle. So I personally prefer the shell models a lot over all the other models these days because it's really, really good. You can just do a very good model, realistic model for anything. So this is the spine model, the beam model session with modified supports. So you can have a model with the end support shifted. The whole deck can be modeled as one beam, and then you can model the bridges. You can have the frame model of the bridge with the simplified rollers and pin. You can have a grid model. You can have a frame shell model where the girders are framed with shell with the offset of the support. Please note each model is different. Something has been, like for example here, the offset from here to here has been modeled correctly. From support to deck is modeled. But the beam is not offset really. It is still part of the shell, but the supports are offset. Right? You can have a full shell model with the correct location of the bearings, and you can have a beam shell full models you can see from here. Everything is complete shell. You can get the stresses in the whole thing in one go. Or you can have a simple frame model that I showed you earlier. Right? All these are for real bridges that we get, and we normally create more than one model to cross-check because it's quite possible to make mistakes in a complicated model like this, but not so possible to make many mistakes in a simple model. So the results from the two should be matching, more or less, cannot be totally different. So the global response should not be much different. So it's easy to check. So normally whenever you do complicated projects, we always recommend you do a complicated bridge and complicated model and a simple model and a WL square by 8, always, to cross-check that the results are correct. Because in any bridge, this moment can still be calculated by WL square by 2 or WL square by 8 or whatever formula is right. So you can just quickly check that approximately that should be the answer. And the bending moment in the column can also be checked by PL, PHOL. So all the calculations manually roughly can be done, and the final results should not be much different. Right? So you might be saying if you can use WL square by 8, why bother with SAP and all this program? Because that is global. It cannot give you a detailed answer for each component, but you can check the total group. As you can see from here, the whole bridge model with the stresses and foundation, everything can be done nicely, neatly. And you can do in one go all the things, and you can check the stresses, you can put the pre-stressing, and you can do the whole bridge. This is a bridge again in Bhutan that we did many years ago. This is a bridge in Nigeria, and the problem here is that the bridges are coming and there's a complicated change. So you model all of this, many piles, many things. So you need to create complete bridges of the ramps, of the slab, of the transfer, right? Everything. So you cannot convert them into simply beam bridges because they are complicated geometry. And if you use shell elements, you can model them more realistic. In fact, this is not a very good model because we still replaced the supports by a fixed or a pin support. Actually, we should continue to model. But in large bridges, we create several models. You cannot create just one model. Different models for different purposes because every model is correct and every model is not correct. So you create several models for each purpose, for the purpose that you want. For this purpose, I will use this model. For this purpose, I will use this model. For example, the foundation modeling may not affect the deck so much. So this model is good for deck. When we come to substructure, we will model this up. So we keep making simplifications and creating different models with different mesh sizes and different things for different purposes. So it's not uncommon to have many models for the same bridge. This is a closer view of that bridge model. This is for the curved bridge, normal 3 bridge, variable girder. And sometimes you can have the spine or the model, you can have cross girders and with links. So people can create for the even big bridges, like cable straight bridges, people first do a simple model quickly, a spine model, just to get the overall response before they rush to the detailed model, because you need to estimate the sizing, and that you can do from a simple model. And once you know the basic sizing, basic properties, then you get the preliminary design done on a spine model, or a simple model, or a line model, or a frame model. Once you're done, then for the final design, you move to a more sophisticated model. Otherwise, it will waste a lot of time. So first model can always be a beam model, simple frame model, 2D model, beam, and then you get overall response, get the section dimensions, then you go to the next level and make a refined model. So, what is the steps for a beam and girder design? Of course, for this bridge course, we are not designing cable straight bridges. We are just designing simple bridges because that requires many courses. But let's say that if you want to design a simple girder bridge, 90 something percent of the bridges in the world are of this type. Only 10% bridges are of the other type. So if you learn this one, you should be able to handle 90% of the bridges. Today we just got a project from Sri Lanka for a 5-kilometer bridge that we will be working on. So maybe I can share with you once we get more details about that. Okay. So develop the general sections. That means cross sections of the bridge, summit dimensions, everything. Then develop the typical sections. What does it mean? Develop the general sections and typical sections. See, bridges are long, like I said, 5-kilometer bridge. You cannot expect to model 5-kilometer bridge in your real project. It cannot, impossible. So you develop the overall bridge, then you say what are the typical portions, how many typical types of portions are there. So this 2-span repeated 20 times, so I will model it 1 time. This one. So you divide the overall bridge into typical bridges or typical parts that will be repeated many times. So in a bridge outside the city, mostly it can be typical. A bridge within the city, typical is difficult because everything is different. You have seen the bridges have to move up and down, so typical is very difficult. But normally we try to identify what elements are typical. Then from typical, then design of RC concrete deck. So we start with the deck first, then we go to select the resistance factors, various resistance factors for the design purposes, select the load modifiers, then select the load combinations, then calculate the live load factors, then investigate the service life limit and investigate the strength limit. So typically we go into that step by step into the design. First do the overall design, then do the basic design. From that you will select all, this is based on Eurocode or British code, ACI will have a slightly different method, but overall this procedure will be followed, right? So number 1 is select overall geometry, typical design, deck, especially finalize the deck because that will bring all the loading, and after that you calculate various types of factors needed for the bridge design which depend on the deck dimensions, and then you carry out the rest of the design. And for serviceability and for strength. For slab bridges, same procedure. You can read that. It's almost similar. Minimum depth requirements, live load. Then, because it's a slab bridge, then you investigate the reinforcement distribution, investigate shear, check for minimum, maximum dimension, and so on. So you have simple and simplified procedure for different types of bridges. Okay. Handling pre-stressed cable. This is an important and interesting part. Conventional approach is that the pre-stressing is considered as part of the design as a reinforcement. But actually pre-stressing is really a load. on the bridge or on a girder. It's not a reinforcement. It's also a reinforcement at ultimate stage, but at surface level, it's a loading. And that is very important because it changes the stresses in the whole bridge. So if you have pre-stressing, you will get different moment. If you don't have pre-stressing, you get different moment. So you cannot design the pre-stressing for a moment which does not include pre-stressing. So pre-stressing must be estimated and put in the analysis first, and then if it is not enough, you need to change, run again. So pre-stressing actually puts a loading onto the bridge or onto a structure. Conventionally, single element approach is like this. What you're studying now, probably that you have a girder or a beam, and the load is applied on that, and you put the pre-stressing in there, and then pre-stressing puts a force and induces a negative moment because of the eccentricity of the force here, which balances the positive moment in terms of the stresses, right? This is for a single element, and that's how it will look like. So the stresses created by bending moment from dead load are added with the stresses created by pre-stressing, and then this and this are added together, and this formula can be used. So this is the basis for pre-stress design, that you add these stresses on the cross-section from pre-stressing and add them or subtract them from the stresses caused by the loading, and ultimately you get the final stresses. That's the way the conventional or a single element pre-stress work if you just want to do one beam at a time. But if you want to do the whole structure, then the situation is different. The situation is that when you apply a pre-stressing on a bridge or a beam which is continuous, then the curvature of this pre-stressing, when you pull it, it pulls forces up and down on the structure because it's trying to straighten, and you're putting it, you're making it curve. So obviously when you try to pull it and make it straight, it will try to be straight and put forces, upward forces here, downward forces here, upward forces here. And this creates a loading on the bridge which completely changes the moment on the girder first, also changes the reactions. This is called the hyperstatic reactions or hyperstatic loading or load balancing. So basically the idea is that the pre-stressing is basically converted into load. So for the analysis purposes, this pre-stress is converted into a load, and then pre-stress is removed from the model. And then this load, pre-stressing load case is simply added and subtracted with other load cases, and that's it. As simple as that. So that's how we can handle pre-stressing in a structure. But the problem is that pre-stressing on a bridge is not done at one time. It is done in stages. You have seen the bridges, they are done in segments. Each segment is placed, then one stressing, second segment, second stressing, many stages of stressing. And it also has losses over time. Every time you stress a cable, it loses some of the stress. So it's a very complicated process. Every time you pre-stress something, the previously pre-stressed bridge loses its stress because that becomes slackened. So you have to go back and pre-tension it again, and so on and so forth. So bridge pre-stressing is a complicated process done in stages, many cables, many locations, and so you must create hundreds of load cases. Each cable must be a separate load case. So you can add each cable at different stages and add that load, and then combine it with the other loads. So main trick is to create the stages of the loading and combine them with the stages of the bridge construction. At what time a particular cable is stressed and what part of the bridge is present at that time is important. Otherwise, pre-stressing cable can pull the whole bridge up, negative displacement. If you go on this bridge, Longmont Tollway between airport and Future Park, if you drive very fast, like I drive sometimes, you can see the click, click, click. You can feel the bridge is not straight. And it is not deflected downwards, it is deflected upwards. So at the pier, there's a dip, In the center of the girder, there is a, because they over stressed it, and long-term deflections have not brought it back to the level that they thought it would come. So it is upward now. Right now, the camber, the deflection is upward at this time. In another 2-3 years, it might become flat. But in the beginning, it used to be more. Now it has become less. Now when I drive, I can feel it less. I used to feel it much more 3 years ago, 5 years ago. So that is something that has to be done. Pre-stressing stages, and then long-term effects and deflections and what load is applied. If they remove the surfacing, the bridge will go up. Right? So certain dead load is needed to keep it straight. So pre-stressing, because it's a load like this one, it can change the entire deflection and long-term stability of the bridge, and needs to be handled properly. So the pre-stress force that applied to the full structure model, the secondary effects are automatically included. Load balancing analysis is not required. Effect of pre-stressing on the entire structure is evaluated in stages. Continuity, stiffness, shortening, shear lag, eccentricities. It's really a most complicated part of the concrete bridge is to handle pre-stressing properly, because it has long-term effects. It can change the reactions on the bearings. It can change the deflections. It can change the, if the segments have been put together, if the pre-stressing loss, bridge can fall down. So there are many consequences of not handling the pre-stressing properly in a bridge. It's way too advanced to be covered in this course. So effects of sequential construction, stage pre-stressing, etc. can be and needs to be handled comprehensively by using this concept. So main task of the good bridge program is automate this whole process. So you tell the bridge that I'm going to construct this bridge in 20 segments. So it will automatically calculate how many pre-stressing you need at each stage, and it will include that pre-stressing in the analysis. So it automates a lot of that stuff. Otherwise, it is very complicated. If you model the pre-stressing into a solid element, you can also calculate the stresses around the pre-stressing. This is the anchors of the pre-stressing tendons. So when you transfer the force from the tendon to the concrete, high stress is developed in that area. And because of the Poisson's ratio, concrete tends to break. Just like as if you're trying to apply force to a cylinder, it will break, right? Same way this concrete can break. So you have to put reinforcement around that to contain and confine this area. So that can be calculated by using either approximate formulas or finite element modeling. Okay, so let me just stop here. So I just gave you this overview of how the bridge is done. And if you are interested, we will come back to it later. But I want to stop the bridge at this time.